Okay, right. Okay, so it has an array that is 28 by 28 by 1, so that is our image. And it also has and it also has our label, which is 4. So again, this is like a numpy. I have to go all the way up. Right. So this is like a numpy array, and this is like the value of the array, and we can again, so as you can see that we have curly braces here, which means that it is a dictionary, and we can again separate it out. So we can do image comma label equals to data image, and then data, go back to where it was. So this thing is called label, and it was also in the feature or like the dataset info on top. So you can see that you have the keys over here. So you have image and label, and that's what is inside the data of the dataset. And we are just gonna print the label here, and the label is 4, which doesn't really mean much. Okay, so okay, I'll just get the list of labels. So labels should also be inside the dataset info, and so if we go to dataset info dot features, right. So these are the labels that we have in the dataset, or these are the images or the classes that we have in the dataset. So we have t-shirts and trousers and pullovers and dress and lots of stuff. So you have all these classes. Okay, guys, we just should just like visualize the data set, because I think then you'll have a better understanding of what exactly is in the data set. So we are just gonna plot the image as well. Also, if you print the shape of the image, then you can see that it is 28 by 28 by 1. So again, when we say that it is 28 by 28 by 1. So normally our images are color images, but this basically means that it has only one channel. So when you say that it is a color images usually have 3 channels, like red, green, blue. And if it's a grayscale images, then it only has like one channel. And so it's basically like a binary image at that point. So we can just plot this thing. Right. So what does this mean? This basically means that we are trying to plot an image, and we want to plot all the rows, we want to plot all the columns, but we only want to plot the first channel. So this is basically equal to 0 by 228, from 0 to 28, and then only the 0 thing of this thing. And then CMap is like the color map. So color map is basically like how you want the graph to look like. So if we just run this, then you can see that this thing is like a shirt. And if you print the label as well, and our label is 4. So which would be 0, 1, 2, 3, 4. So this is a code. And okay, so if we didn't use like a color map, then it would basically show it in like a different color. So that's why you use a color map. And if you only plotted like first 10 pixels, I guess. And I don't know what that is. Also, if you are using Colab, then it will output stuff over here, but the way it outputs stuff is like not how. So okay, normally if you were to run it on your computer, then this would pop up like an image, but in Colab it doesn't do that. So you will just add this line PLC.pause. What it will basically tell. So before, if you don't add that line, then it will draw an image, and then it will draw another image on top of the image. So it will just show you the image that you added the last image that you added. But if you add the PLT pause, then it will basically add an image, and then it will pause, and then it will add the other image. So then you can see multiple images at the same time. But basically, if you look at this thing, then we can see this is the code, and the first 10 pixels. So this is like the or this image is printing the top 10 pixels, so or the 10 by 10 pixels, so which would be the shoulder-ish area. So again, that's like one of the things with computer vision, that for us human beings it is kind of easy to tell what you are looking at, because you can see the entire thing in one go, and also because our brains are smart. But for computers, again, this thing is just an array, like it is a bunch of numbers. And when we are dealing with computer vision, or when you're trying to solve this problem in like a mathematical way, we don't really have the entire image, or we don't really have the, well, I guess we could do that, but in general we don't treat the entire image as like an image. We will deal with portions of the image, and then we try to find patterns within the image to solve it in a more logical way. So in a classical computer vision, you could probably do like if else or something. So like if you have these patterns in the image, then it means that it's a dog or a cat or something. So that's like a more heuristic way. But in this way, we are doing it with machine learning. So it would be more like you are trying to find a formula. And so it's like a formula where you have f of x equals to y, and you give it an image, and it will output what the image that thing is, in very simple terms, basically. So we have your class labels here, and we can just print what the class label for this is directly. So class labels is like an array, and label is like the indices, or like the index, and so you can just pass like the index to the array, and then it will print the actual label. Okay, so we will just like print first 5 images or something. Okay, so we have a coat, then another coat, and then an ankle boot, a sneaker, and a sandal. So again, this is like a very simple data set. It's very small, like 28 by 28, and it has only the image and then a white background. Normally, if you look at the real world, then you have your background and everything. So like if you look at my room, which I won't show you, but it's basically a mess. So it's hard to find stuff in the real world. But this is like a very simple example. Then yeah, so that's our data set. What else do I have to do? Okay, so now that we have our data set, we can work on the image classification part of it. So for this workshop thingy, we'll be working with convolution layers, and we can also import down with TensorFlow. So from TensorFlow right, so we're gonna make a model that will help us classify the images. And yeah, so let's just do that. So df.keras. So keras, so TensorFlow is like a mathematical library, and then keras is like a high-level abstraction layer that will just help you not do the not do the mathematics of it. So everything is kind of already done for you, and you just have to import stuff and then run it. So we are going to have that keras model sequential. Oops. All right, this is sequential. Okay. Right. So again, this is using TensorFlow 2.3. So keep that in mind because TensorFlow changes a lot. Okay, so we can add Alright, so what exactly do we mean when we say a convolution layer? So a convolutional layer basically helps you find patterns within images. So you will give it this image of a sandal, and then it will try to find patterns within that image that will help it understand that, okay, this pattern belongs to this image, this pattern belongs to that image. And then this convolution neural networks are what we call, what we used in deep learning. So what deep learning means is that you just stack layers on top of each other. So it basically means that you are trying to find patterns within the image, and then you're trying to find patterns within the patterns. And again, the more layers that you stack together, the more deep you go. And the more deep you go, the more patterns within patterns within patterns you're trying to find. It is also sort of an abstraction thing where you say that the first few layers are trying to find low-level features, while the last few layers are trying to find high-level features. So for example, low-level features would mean like edges or something, and then you're like, okay, these edges combine together to form the shape, and then these shapes together combine to form this animal, and then this animal belongs to like a cat. So that's kind of how this, like, the concept of abstraction works for deep learning. The other thing is basically the parameters, or what exactly are you passing to inside a convolution. Okay, so for those of you who don't know what a convolution is, it basically means that you have this image, and you are applying an affine. That's called an affine. You're applying like a dot product. Okay, so you have something else like a kernel, which can be. So you have an image, and just think of another image. Okay, so you have this big image that's like 28 by 28, and then you have another image that's like 3 by 3, and then you're multiplying the 3 by 3 on like this tiny portion of the image, and then you just slide that thing across, and that's what we call a convolution, where you have an image and you multiply it with something else, but it's like you don't multiply it. It's like a dot product, but it's a sliding dot product. I don't know what the other. Oh, let's just Google the definition. Mathematical operation produces third function. Okay, but yeah, so it's kind of like a sliding operation where you have your image, and then you have your weights, and you slide your weights, and that's how you convolve in a convolution. What this basically means is that if you look at the parameters here, we have 16, we have 3. Okay, so this is like our filters equals to 16, and then this would be our kernel 5 equals to 3, and then our activation equals to the value. So what we mean here is that you have your image, you have a weight, and you apply that weight onto the image, and it will give you an output. And then if that output meets like a certain threshold, then we say that that thing has been activated. So in terms of like a neural network, it's kind of supposed to simulate how your brain works, where you have like a neuron, and you pass that neuron some information, and if the neuron thinks that, okay, this information is valuable, then it will activate itself. So in this case, we have like 16 weights, and so 16 filters or 16 weights, or they're trying to find 16 different features within an image. And if they can find those features in the image, then they will activate. So in this case, we are using an activation that's called ReLU, which basically means that you have your image, you multiply it with a filter. Well, it's like think of it like a Snapchat filter. We can actually see what the filters are later, but they're basically trying to find some information within the image. So you have your image, you multiply it with the filter, and it will give you an output. And if the result is less than 0, then we ignore it. And if it's more than 0, then we consider it as an activation. Then when we say a kernel size of 3, it means that we are trying to find patterns within like a 3 by 3, or like, so we're trying to find so we consider the image as like separate areas. So you can divide your image into like 3 by 3 pixels. And then within those 3 by 3 pixels, we are trying to find if that pattern is there or not. And then the second layer will then try to find patterns within those patterns of 3 by 3. And that is how we this is what we call like the receptive field of an image. So again, for like a human person, you can kind of see the image in one go, and you just like guess, okay, that's what like this thing is a sandal. And you can probably see that it's a sandal because it also says here it's a sandal, but I digress. So again, so for a computer, it will take like 3 by 3 pixels of this image, and it will basically give you an output, or it will give you one value for every 3 pixels. And then the next layer will then take 3 pixels, or like the 3 by 3 pixels of that image. But the 3 by 3 pixels of the second layer would be like a bigger area for like the first image. I don't know if that makes sense, but yeah. It will make sense eventually someday if you decide to work on computer vision. So also, this example, we are actually trying to follow the tutorial thingy that TensorFlow has, except they use fully connected layers. So the way fully connected layers work is basically you have this image that is like 28 by 28 pixel, and a fully connected layer will try to find the associations for every pixel with every other pixel, which will basically mean that you have your pixel here, or like the top left, and that you multiply that pixel with the pixel next to it, then you do that for the pixel next to it, and you do it then for that pixel, you multiply that pixel with every other pixel in the image, and then you do that for every pixel. So that is computationally intensive, and it also gives you like a lot of noise. So it's like, let's say that you have patterns, but you can have a lot of patterns within an image, but some patterns are very useless. So you don't really want all the patterns that might be there in an image. So a fully connected layer will try to find associations of every pixel with every other pixel in the image, and it can also find like a lot of noise and stuff. So find patterns that are like useless. So you also don't want to learn everything. So for example, in convolution layers, we'll be only learning about 16 filters. So we can compare our results with this approach as well. So so you can see that they also have the data set, and then they try to visualize the data set, and then they have a model, blah blah blah. We will be also doing that, but then they get an accuracy of about 88%. So we will try to beat that by using convolution neural networks. Okay, so back to the model. Okay, does anyone have any questions? Prefer notebook for anyone of us. Oh, okay, great. Okay, so yeah, so basically we are going to pass an image to this model, and this model has 2 layers. So the first layer will try to identify patterns within this image, and the second layer will then try to identify patterns within the patterns of the previous, or like, it will try to find the patterns within the patterns, and then you flatten that. So flatten basically means that, like, right now it's like an image, but so an image is like a 2-dimensional or 3-dimensional, in this case a 2-dimensional, so it's like a 2-dimensional vector, and then you just flatten it, so it is then just like one array. So you can also do it, I don't know, so this is what it looks like if it is like a 2D image, and this is what it would look like if it was flattened. Oops. Right. So yeah, like that's how flattening works basically. But you have, oh, you can actually see it because it's too small. I thought it'd be bigger. But okay, so the point is that now it's like a one-dimensional array, and they took this image and then they flattened it, and because the value of every pixel is, maybe it would be better if we do like to be, point is, okay, you flatten it and then it's like a 1D array. It would be so this is like a one-dimensional array or like a 1D vector, and then you can see that it has like, it's a vector of 784, or like an array of 784. Yeah, like an array of 784 size, and this is like the value of every index. It's a very horrible way to represent it, but it basically tells you that this image is basically this thing. So if you flatten it. Many wonders of computer vision. Okay. So again, so we can see what the output of the convolution, or like what are the outputs of like our pattern generating thingy are, and then later we can see what happens if flatten them. But again, like flattening should be like a very obvious thing, hopefully, that again, you have an image and you flatten it so that it's like a 1D array. And then because we have like 10 different classes, we will output 10, like a network will output 10 things. This will output the probability of it belonging to that class. So you have 10 neurons, and like a fully connected layer is basically like a bunch of neurons. So you and a dense layer is a fully connected layer. So this is like interchangeable terms. And so basically this model will have 10 neurons, and every neuron will tell you what class it belongs to. And we don't have softmax. So a ReLU activation basically means that if it is 0, then don't activate it. If it's more than 0, then it is what it is, or you activate it, I guess. And a softmax activation will normalize the outputs between 0 and 1, so that is more like a probability. So then, if class 1 has a probability of 90%, then the rest of the classes will add up to 10%. So it is, yeah. So we can then compile this model. So also, like when we say a model, it's basically like a formula, and it's a formula. So for like, if you want to find the equation of a line, it will be like y is equal to mx plus c, right? So this is also like a formula, but it is one that would normally have like just like a very small model, but a normal model would have like millions of parameters. So you can think of it as y equals to ax plus bx plus c y or whatever. But it's like a formula, like a very, very, very big formula with millions of parameters. And because it has so many parameters, we don't really know, or there's no way for us to interpret that model, which is why it's called deep learning, because it is deep because there are multiple layers to it, but it's also deep because it is too big for us to interpret or for us to understand what is actually what the actual model is, because there are just so many parameters in the model. So this is a formula essentially that was generated by the computer. And so it's a formula that was generated by the computer, and we have very little understanding of what the formula is or how it works and stuff, which is why people are kind of terrified of what AI can do in the future, because you don't really know what's happening. But yeah, so we will just compile the model. So optimizer equals to so optimizer is basically what will optimize the model for us. So when we talk about how deep learning works for a model, you can just think of it from like a random search function point of view, where you have this model or you have this formula, and this formula is like a random formula, okay? And you 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 have a random formula and you give it an image, and it will give you like a random output, and you find the difference or you find the error between what the output was and what the output you expect, and then you try to tweak your formula so that it will be more closer to what you actually expected the output to be. So I don't know if you have seen, like, there's usually like a mountain graph kind of thing for it, but it basically means that the way this works is basically you have a formula, you give it an input, it will give you an output. You tell it, okay, I wanted the output to be 10, the output is 1, so difference is 9, so tweak the formula, and then you just keep trying it again and again and again. So this is what the optimizer is. Optimizes the function to reduce the error, and by reducing the error, we approximate the function to what it actually should be. And then a loss function. So the optimizer, it is what optimizes the model, and the loss is what we are trying to optimize. So the loss is like the difference between the ground truth, or what the actual thing should be, and what your current output is. And to identify the error between the output and the ground truth, you have to know how to calculate the error. So that is then calculated with the loss function, which would be so the calculated cross entropy loss basically tries to maximize the likelihood of it being one class. So if it is that class that you were expecting, then it will give you, it will say, okay, good job. And if it's a class that was, so if you wanted the class to be pants and it was like shirt, then it will say, okay, no, you're doing a very bad job. This is the error, go fix this error. And then the optimizer will take that error and it will tweak the formula, and then it will try to make sure that if you give it that specific image another time or again, then it will try to give the output as pants. And that's basically how all of deep learning works. Okay, so now we have our model. We don't have a model. Okay, so okay, one bracket. Yeah, okay, so now we have our model and we have our data set. So our data set is again images, or about 60. So we have about 70,000 images, out of which we are going to give the model 60,000, and we're going to keep 10,000 for ourselves to verify that the model actually works. And so this is what the data set looks like, and we are now trying to train the model. So before we actually train the model, we will also do a bunch of pre-processing on the model. So yeah, I guess the best way to do it would be just do it on the data set. So just create a function that's called preprocess, and we pass it the data, and then we get the image, data image, comma, data label, and we can do, sorry, so an image will have pixels, and in general, pixels have a value of between 0 to 255. So for example, if you have a color image, then it will have like a red value between 0 to 255 and a green value between 0 to 55 and a blue value. And it's like paint. And so like you combine these different colors of red, green, and blue, and it will give you one color. And that one color is one pixel. And then if you make up the entire image of a bunch of pixels, then that gives you the actual image. But basically, so every pixel has a value of between uh, 0 to 255. So we can normalize that to a range of between 0 to 1 by just dividing by 255. That just helps the model a little bit. If you normalize the data, it just helps the model a bit. For a neural network, it's the mathematical model, so it will be like, okay, 10 is greater than 0, so I should give more preference to 10 because it's math, which is why we try to normalize the data, if that makes sense. And there is no need for any further processing. And we can, not do anything else. We can also actually do more stuff. So because right now we have about 60,000 images. So when you're actually working with like models that you want to deploy in real world, you will generally use millions of images. So for example, if you look at Uber, okay, so Uber is trying to come up with a self-driving car so that they don't need drivers anymore. And if you want to make sure that your self-driving car can actually work in the real world, then you need a data set that will include everything that's in the real world so that it can take all kinds of scenarios and stuff. And so they train on millions of images, and I think their monthly budget is about like 5 million. I don't know. So they basically spend 5 millions on collecting data and testing their data, blah, blah, blah. So again, we are only dealing with 60,000 images. So one way to increase our data set is we can take this image and we can flip it horizontally, we can rotate it, we can perform augmentations to the image. So we take the same image, but then we modify it a little bit, and now it's a different image. It's like a new image. So we have technically added more data to our data set. So even though we are working with 60,000 images, we can convert them to like 120,000 by just flipping the images horizontally. So we can do this with another model like this. So preprocess. That's sequential. And layers, experimental, preprocessing dot random flip. Okay, so what this layer does is, so it will randomly flip the image with like a 50-50% probability, and it will randomly flip it horizontally. Okay. Yeah, so you give it the image, and there is a chance that it will then flip the image, and that chance will basically increase our data set, because normally 60,000 images is not it's just not a lot of images, but because this is a simple data set, you don't really need like a lot of images. So we can also add this to our okay. And then we have a preprocessing function here. We can also, if you wanted, you could have also added it over here. So here preprocessing and then you can do scale equals to 1 by stuff. But because we are doing it there, it doesn't make sense to do it here, but you can do it anywhere you want basically. So again, we have a function that does the pre-processing of our data set, and it basically takes the image and it divides it by 255 so that our image, or our new image, will be somewhere between 0 and 1. And so we can then take our train data set that we created before somewhere. So before we basically took the data set and split it between training and testing, and we will train data set, and then we will map or you apply the map. So what map basically does is it takes the function, it will take this function, and it will apply it to every element in the data set. And then this will take like a buffer size of 100 and it will shuffle between that buffer, and then we can batch it. So a batch basically means that so again, we have like 60,000 images, but we can't fit 60,000 images in our memory and stuff and still work on it. So normally what we do is we will divide those 60,000 images into smaller batches of 16 or something, and then we work on that. So yeah, so like you just do 60,000 by 16, and that is the number of batches you get, and then you train with every batch. And for a test data set, again, we will do test data set preprocess, and we don't have to shuffle it because okay, so the reason that we shuffle the training data set is because again, this model is designed to learn patterns, and if you don't shuffle your data set, it could actually just learn the order of images. So it will know that, okay, the first image was the pant, the second image was the shirt, the third image was a trouser or something. So again, so this network is learning patterns of patterns, and it's trying to identify correlationship in the data set, and it can just memorize the order of the items in the data set. So you have to make sure that the things that it's learning are actually what you want it to learn, which is why we keep shuffling the data set so it doesn't learn the patterns or the order of the data set. And so we have our training data set now, and we have preprocessed it, and then we have shuffled it, and then we have batched it, and then we will just train it. So we just do model that fit, or actually we will also add a matrix here. Matrix equals to so you have to make sure that all your code is you run all your code cells in like a sequential manner, because you can run it in any way you want, but so it won't work then. Okay, so model.fit, and then we fit in the training data set, and we will have epochs equals to 10. So again, we are training the model on our training data set, and when we say an epoch, it basically means that one epoch is one entire data set. So again, we are dividing our data set into smaller batches, and when we say one epoch, it means that it has trained on all the batches within one data set. And we take our model and we train it once, and then it gives some results, and then we give the data set, or we give it the data set again, and then it iteratively improves it. So you train a model, then you give it the same data set again, then you give it the same data set again, and then it will just improve its results and stuff. And then to validate it, we can actually just pass the test data set here as well, and it will just directly tell us how it performs on the test data set. So now it's basically training the model. And when you say one epoch, it basically means like the first iteration of the entire data set. And if we go back to the one network that was using fully connected layers, where it was trying to find the association of every pixel with every other pixel, it will also learn like some stuff that we don't want it to learn. It gets an accuracy of about 88%. and in our case, we are getting 88 in like the first iteration. So like the model is still running, learning right now. Okay, that is more or less just of it. Okay. Are there any questions and stuff? Oh, there are people typing. People adding. Okay, I have no idea. Also, that is a big part of neural networks or deep learning is waiting for your network to train. So normally you would have like computers that are very, very powerful, but even then, most of your job is just like you train a network and then you just sit and you wait for it to train, and you don't really have anything else to do. So yeah, so like compared to like a normal programming job, I guess, where you have to write code. I don't know how much code you have to write like a normal job, like 100 lines of code every day. But in Python or like for like deep learning and stuff, you don't really write a lot of code. It's mostly maths and stuff. But the maths and stuff is already kind of there, so you just need to have like an understanding of stuff. But yeah, so you don't really need to do a lot of work. That's basically what I'm saying. If you work in if you work with neural networks. Okay, so we can see that, so every epoch is basically this is passed through like the entire data set, and then we are giving it the same data set 10 times. So it trained. So after one epoch, we saw that we got accuracy of 85% on the data set that it has seen. So, and then it gets 88% on the data that it has not seen. And then we take that model and then we train it again with the data set. And then it improved the accuracy on the data set that it has seen from 85 to 89%. And so, and it also improves it on the validation accuracy, which means that the network that we are training right now is generalizing, or in the sense that it works on the data that it's given, and it's also working on the data that it has not seen before, which means that it is something that we can actually use in the real world. And then as you can see that, as we go down later, it's giving us 94% on the data that it has seen before, but it's only giving us like 90% on the data that it has not seen before, which means that it is learning some stuff, that's learning some features or something that are only there in the training data. It's not there in the real world. So now we would then try to investigate what is there that is only there in the real, or that's only there in the training data set, and how can we improve its performance on the real world. So that is why we have the validation data. So it is to validate the model in the real world. And normally what you would do is you would split the data set into three types. So first is your training data, then is your validation data, and then the test data would be like a third category. So for example, like the validation is a second level of validation where you can see that you're getting this. So for example, in this case, it would make more sense to choose the ninth epoch of this model, because we saw that after we trained the model 9 times, we got good validation accuracy, right? But it could also be just like like coincidental. So then again, we tested on the third data set that is also not seen by the network, and then it gives us just like a better validation of a model, how reliable the model is. So yeah, so that is basically it. We have trained the model. So again, it's like a very, very simple thing to do. This is like a very simple example where we had the data set of clothes and stuff, and then we trained it, and we are getting about 90% accuracy, and then we can try to run our network by just taking the data set again. So for results, results. So, okay, so we kind of already know what's there in the data, so we can do image comma label equals to data image data label, and print our PLC data. color map equals to plc.cm.binary. Okay, great. And then we will preprocess it. So image equals to preprocess, and image, and then model dot predict, and we give it this image. Okay, so one thing we need to do here is we still need to batch the data. And what we mean to batch the data basically means that we still have to give it like a subset of images instead of an actual image. So you would actually need to do result images as an array, and then you have to put, because the model expects a data set, and a data set is basically a bunch of images. And so even though it is only one image, it would mean that it would have to be a data set of one image. What that basically means is that you take an array and then you put the image inside an array, and then you give that array to the model. So if we do results equals to and then we can do images. Oh. We don't really pass the image to the preprocessing. So basically you can see this is like the shape that it expects as an input. So it wants 4 dimensions. The first dimension should show it like the number of images within the data set, and then the image height, the image width, and the number of channels in the image. And yeah, so we don't really need to create an array and do all of that. We can just basically just add like another dimension to our image. So if we do here, image the shape, you see that it is 28 by 28, blah, 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 and then we can just do image equals to, oh wait, just work. Oh, okay, because never mind. We can do image equals to np just add like a dimension over there. So print image to shape. Yeah, so the original image shape was 28 by 28, and then the new image shape is basically 1, 28, 28. So basically added like a 1 by adding like a dimension to it. And this is again like a Colab thing or like a Python thing where we have removed the code, but it still syncs and the code is there. So, but it's whatever, right? So now you can see that it works, and if you don't do that, then it wouldn't work because it expects a data set. And by a data set, it expects like a number of images in like the first dimension. Okay, so if we do output equals to model to predict, and then you print the output, it will give us the probability for every class. So we have 10 classes in the data set. So these are like 10 values. And so it tells you that actually maybe one, two. Okay. Let's do it manually. Why do I not have a delete key? That makes no sense. Output, I'll just write that. So we can see that so we can okay, never mind. Okay. So we can see that we have like 10 classes, and it won't show you like ideally you wanted to show every like 0, 1, 2, 3, 4, 5, 6, but it doesn't show you that. But we can see that it has a high confidence that it is class 4, and it has a low confidence that it is class 6, and it's absolutely sure more or less that it's not any other class. So that's like one more thing where if you look at our actual class labels, where are our class labels? Right, yeah. So as you can see, we have our class labels as t-shirt, trouser, pullover, blah, blah, blah. But again, they don't really mean anything to the computer. So what you do is you assign a number to all the classes. So this would be like 0, 1, 2, 3, 4, 5, 6, because, you know, like for a computer, it doesn't really care if it's a bag or a shirt or whatever. So you assign it a value, you assign it a number. But even then you have a problem, because then if you have like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or actually 0, 1 is, it is only till 9, but whatever. So if you assign it a value, then 9 is greater than 0, right? Or 9 is greater than 8. So if you assign a mathematical value like that, then it will have a tendency to only predict 9, because 9 is like the bigger value. So again, what you're gonna have to do is you sort of convert that value to binary, where you just write 9 as binary, or like combination of zeros and one. But again, that is something that is done internally by TensorFlow right now. But the point is that you have to make sure that your labels are not actually used as labels, because it doesn't really care if it's a short or something, whatever. So you have to take your label and you have to convert it to a value that would be like an unbiased representation of the class or of the labels. So again, we can see that this gives us a probability for all the classes, and then what we basically do is we will take the output as the index of the array, or we'll take the index of the maximum value in the array. So then output will become the index of whatever is the maximum value of output. And if you do that, then it will throw an error because it can't plot it anymore. But now we can see that the output is 4, and then because we already have an array called class labels, we can just pass the 4 to that thing, and it will print the class. So we can just do it class, or I don't know. Also, these are like F strings in Python. They are like in Python 3.7 afterwards. So if you try to use it before Python 3.7, it won't work, but it basically allows you to do, you can print anything you want easily. Like, yeah, it's something if you're interested in. But again, you can see that you have your code here, and then it identifies that as a code, and it may not. So again, we only have like 90% accuracy, right? So it will not do it for every class. So what we can actually do is print this as predicted, and print actual, which would be label. Okay, and then we also need to pass that to class label. Okay, but if we do it for, okay, let's do it for like the first 10 classes. we can see that code, ankle boot. So it identified that ankle boot as a sneaker, or sorry, it identified the sneaker as an ankle boot. So again, it works most of the time, but there are like 10%. There's like a 10% chance that it will be wrong. So yeah. But again, if we go back to this, the one that was using fully connected layers, where it was trying to find association between every pixel, it was like 88%, and from 88% we went to like 91%, and you can tweak the network, so you can probably add like more convolutions. You can make it deeper. You can do all sort of stuff. Again, so if we go back to our model. So again, the first layer was trying to find 16 patterns within the image, and then the second layer was trying to find 32 patterns within the first 16 patterns of the image. So we can just like add more layers and stuff, and that will change our results. If 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 the second pattern has stuff that the thing can learn from, then it will improve our little results. And if it tries to find more noise, then it will just decrease our results. But yeah, that is pretty much it, I guess. I think we're already over time. So yeah.
So if anybody has any questions, last moment questions, we can take them probably now. Anything? If anybody wants to ask, they can just unmute themselves and ask. Otherwise, we can also share the link to the recording and the Google Colab file, which I already sent in the chat. I think everybody is clear. That means, and we can probably just send more detailed information later after the talk. So if anybody wants to follow up with that, they can do that. And if you have any other questions, you can just send me the questions, and I'll make sure that you have the answers. So yeah, I think that's all then. Sorry, but what does the bar graph represent?
So the bar graph represents like the probability for every class. So you have 10 classes, and the output of the model is the probability for every class. So it's just trying to plot the probability, and the bar graph is the probability. So it's between 0 and 1.
Yeah, I think everybody is clear now. And if anything else is unclear, just ask, or you can just email the questions to us. Yeah, I think everybody's cool then. Okay. Thank you. Thank you to everyone for attending, and thank you so much, Tejas, for the workshop. I think it was really good to just get an understanding of how things work. And if anybody wants to do something follow on in the future, and if you don't know where to start, then you can also reach out to us. And we can probably come up with more event ideas for the next workshops.
Okay. Thanks to Survey for organizing this, I guess. And I guess that is pretty much it. So yeah, bye-bye.
Bye, everyone. Thank you.